Today we are looking at testing differences of two means with independent samples. We just got done looking at dependent samples. The difference, dependent samples, everything was the same except what we are observing. With independent samples, they're going to be two totally different populations. It says that we say that two sampling distributions are independent if there is no relation whatsoever between specific values of the two distributions. So you got to pay attention to that before we decide what type of distribution we are using. Are we using just the t-test because we have a sample that is the same people or the same individuals, or do we have two different samples of two totally different groups of individuals? A little bit different view than dependent samples. Our null hypothesis is going to be mu1 equals mu2, so we're saying that the two populations are exactly the same. There is no difference in them. That's different than in 9.6 where we said it was equal to 0, where there was no difference in that one population or that one sample. The alternate hypotheses along the same lines of 9.6 can be less than 0, greater than 0, or not equal to 0. If the differences in the populations are less than 0, that means mu1 is less than mu2. That's a left-tailed test. If the differences are greater than 0, then that means mu1 is greater than mu2, and that's a right-tailed test. And if we're just concerned that there is a difference and it's not equal to 0, then that means mu1 does not equal mu2, and that's a two-tailed test. For large samples, the critical values are the exact same as in 9.2. We'll use those 6 pictures, but in our calculator we'll use 2-samp z-test. And small samples, we're still going to use the student t-distribution. However, make note of this, the degrees of freedom will be n1 plus n2 minus 2. n1 plus n2 minus 2. So rather than just subtracting 1 from n, we'll add them and subtract 2. Alpha with 1 apostrophe and alpha with 2 apostrophes are the same, and we'll use 2-samp t-test. So let's look at the first example. A company executive is interested in the average number of years salespersons have been with the company compared to the average number of years for office personnel. A random sample of 12 salespersons show that the mean number of years with the company is 3.2, with the sample standard deviation of 0.6, and a random sample of 19 office personnel showed the mean number of years with the company is 5.6, with the sample standard deviation of 0.2. Do the data indicate office personnel tend to stay longer? So we're going to call salespeople mu1, and we'll call office personnel mu2. So our null hypothesis is that mu1 equals mu2. There is no difference. Our alternate hypothesis will be, do the data indicate office personnel tend to stay longer? So that office personnel is greater than sales people. So that will be mu1 is less than mu2. This is going to give us a left-tailed test because it is less than, and again, when you're thinking of this, think of in terms of the first population. If the first population is smaller, that's a less. If the first population is a greater, then that's the greater than. A lot like we did in 9.6 with the before and after. And our level of significance is 5%. Since both samples are less than 30, I'm going to use t. And my critical value comes from my chart. So my n is 12 and 19. So my degrees of freedom will be 31 minus 2, so 29. So to find the critical value, we go to our chart. We are 1 tail, 5%, and 29, so 5%, 29 is 1.699, actually negative 1.699. We draw our picture. And then we run our test in our calculator. When we run our test in our calculator, we go to stat. This is going to be T, 2SAMP t-test. I highlight stats. I type in the info given in the problem, so 3.2 and 0.6. And we had 12 salespeople. This is 5.6, 0.2, and we had 19. mu1 is less than mu2. We will always highlight pooled, yes, calculate. And so we get a really big or small t. T is negative 16.2 and P is 0. So that lets us know that we reject H sub 0, and office personnel stay longer than salespeople. To quickly go through two, again, we have two populations. We have freshmen selected at a large university. There's 63 of them. They have a mean of 51 and a standard deviation of 1.2. We have another population of 45 females with a mean of 54 and a standard deviation of 3.1. We want to test the claim at the 5% level of significance that females score higher. So again, we'll make the claim that they're the same. We want to test if the second population is greater than the first. This is now a z-test, so this is still left-tailed, 5% level of significance. This is a z-test, so we'll go to our chart and we will choose 5% level of significance. Left-tailed would be negative 1.645 is our critical region. And picture. And then again, we go into our calculator and we will enter in the pertinent information. Standard deviations 1.2 and 3.1. 51 and 63, 54 and 45. Just make sure that you designate which is population 1 and which is population 2, and notice that there is a little bit difference in the calculator when we are using Z or T, just the way it looks. Again, this is less than 2, calculate, and again we get that relatively big number, negative 6.17, and again a P of 0. So Z is negative 6.17, P is 0. We reject the null. Females score higher than males. That's it.